A very good afternoon to you all. As a part of today's colloquium, we also have a special talk titled Sundials to Modern Atomic Clocks, a brief history, which beautifully connects the evolution of timekeeping with advances in physics. Before we dive into the enriching discussion ahead, may I invite Mr. M. Kishore of 3rd BSc Physics to kindly introduce our resource person, Dr. Ajit Sharma.
A very warm welcome to everyone gathered here. Every scientific journey begins with curiosity and question about how nature works and courage to seek answers with patience and precision. Our resource person today is someone whose journey beautifully reflects the spirit of exploration. Dr. Ajit Sharma, Associate Professor in the Department of Physics at IIT Tripoli. He is an experimental physicist working in the fascinating field of atomic, molecular, and optical physics. For more than 12 years, his work has focused on pushing the limits of precision from frequency meteorology and spectroscopy to cold atom, ions, and emerging quantum technologies. His journey took a decisive turn at Jawaharlal Nehru University, New Delhi, where he pursued his PhD in physics. At that same time, in Raman Research Institute in Bengaluru, he built complex experimental systems from the ground up, transforming abstract ideas into real instruments and successful demonstration and all optical switch using room temperature atomic vapor. Driven by precision, his work carried him beyond national border to the Helmholtz Institute Mainz in Germany, where he led high precision atomic measurement studies and contributed to research addressing one of the most insightful questions in modern physics, the search for dark matter. Today at IIT Tirupati, Dr. Sharma leads the Precision Measurement Laboratory, a space where fundamental science meets the real world impact. His laboratory is actively involved in translation research, developing technologies such as quantum communication system, quantum memories, quantum repeaters for quantum networks, and portable atomic clocks crucial for positioning, navigation, and timing applications. His expertise includes atomic physics, precision spectroscopy, atomics, lasers, and ion traps technologies. Beyond disciplines and devices, his work tells a larger story how carefully measurement and deep understanding can drive the next quantum revolution. With this journey in mind, it is my honor and privilege to invite Dr. Ajit Sharma to the stage to share his experience, insights, and knowledge with us.
I request our HOD ma'am to felicitate our resource person.
So I would like to take this opportunity to thank Uttara Madam for inviting me. I was there in Chennai on a previous occasion upon her call, where there was an IIPT event at IIT Madras, and it was a wonderful event on a Saturday. And now I'm here again on her second invitation in her own college, and it's a beautiful college. I'm very happy to see the campus and meet the students. And so today, what we will try and share some insights on atomic clocks, and so I will try to give you some glimpse on why timekeeping is important, right? So usually, you attend some concert and the person who is singing or performing, they will say, "Are you having a good time?" Right? So I should ask the same question to you, right? Are you having a good time? And so what you can see is that even in our conversations in daily life, we kind of reflect, okay, I'm not having a good time, or I'm having a bad time, I'm having a bad phase, right? So what it is very intrinsic is that time measurement is very critical to human civilization, right? So what I will try to do is I'll try to introduce you to time measurement in general. And so this has been there from very early ages. And what has happened is that with the progress in technology, we have been able to measure time at very, very fine precision, right? And this has led to a lot of modern day technology. For example, a lot of us, we are using mobile phone, we use WhatsApp, we use a lot of other applications. And what's interesting to note here is that any kind of communication network, whether it's telephone, whether it's all these app-based services, they are critically reliant on the modern telecom infrastructure, at the back end of which there is an atomic clock, right? So without the clock, none of this will exist, right? So you pick up a call, and let's say you call your friend, and there are thousands of people or millions of people who are trying to access and reach out to others at the same point in time using the same cable, right? And so how do you do this? Well, essentially you splice the data in very fine data packets, right? And then you send these data packets small amount of delay, right? Now that delay is not perceptible to the human ear because percentage of hearing is only 1/10 of a second. So anything faster than that is great because you don't essentially recognize that delay. Of course, at some point technology was not that mature. So when you used to make an international call and you would speak to your friend in the US or UK, his voice would come with a little bit of gap, right? But now that lag is not there anymore. It's like you are hearing his voice or her voice almost at the same instant of time, and this is only possible because of refinements in time measurement, right? So I wanted to figure out where your college was. So what I did, I flipped my phone out, I put the location on my Google map, and it showed me multiple ways in which I could reach your college, right? So how is that possible? Once again, we have a bunch of satellites which are orbiting the Earth, and interestingly, all these satellites have onboard atomic clocks, right? And so what they do, your app which you are using on your phone, that app connects to the nearest mobile tower, and then it beams a signal directly to satellite, right? And then there is like 4 or 5 satellites which trace out your location based on the time the signal takes to reach those particular satellites. And this, if you think about it, all of this happens in a flash, right? You are completely unaware that such a series of events have actually happened the moment you flipped your app on, right? That there's a signal which went to the station, then it went to the satellite, it came back, it located your position. Everything happened in a flash. So that's the power of technology. That's the power of precision timing, right? So with that introduction, let me just highlight the title of the talk again, which is Sundials to Modern Atomic Clocks, right? So the plan of the talk is that I will try to motivate you on why this is important. Why should we worry about time measurement at all, okay? And give you some background, give you some understanding and feel of the technology, the terminology that is used in precision time measurement. And then I will try to highlight the kind of activities that we are doing in our research group at IIT Tirupati. And finally, I will summarize with some future direction and challenges. So if you look at this slide, okay, here I have a beautiful picture where it shows from like the 3000 AD all the way up to the current generation 2000. And you see a series of pictures which depict some form of clock, right? And interestingly, starting from this is a picture of the Stonehenge in the UK, right? And then you have a lot of other things. So what you see here is that there's a whole bunch of clocks, okay, of different styles, of different precision, right? There's a grandfather clock, there is a small pocket watch, right? And then you see here something called the quartz oscillator, right? This is a quartz crystal, and so it has its own natural frequency of oscillation. So if you were to power that crystal and if you were to tap into that oscillation, that's a beautiful frequency reference which you can use as a clock, right? So this was one of the early technology improvements around 1930s, and then around 1950s the first atomic clocks came into existence. The first one was actually built in the National Physical Lab in the UK, and then there have been continuous improvements on the precision of such clocks. And then in the late 1980s, the US started sending satellites which was armed with these portable atomic clocks, and basically that constituted the modern day GPS, constellation that we know of. Of course, there are other countries who have created equivalent GPS systems, right? So, for example, there's GLONASS. In India, we have NAVIC, right? So, there's this whole series of developments which have happened. And what is interesting to note is that with each type of clock that you see on this photograph, okay, with the improvement in the resolution of time measurement, humankind has taken a leap of faith, and new technologies, new applications have come up, right? So, for example, we all hear about this famous story where Columbus set out to discover India, and unfortunately, he landed in West Indies, right? So, I wouldn't blame Columbus if I was there, because you don't have access to navigation. What will you do, right? You don't have access to maps. So how will you figure your direction? I mean, today's day and world, even if I am in a completely unknown place, in a completely unknown country, as long as I have a cell phone and as long as I have a connection to the internet, I don't need to worry. I don't need to know. I don't need to be a native of that place. I can figure out everything on my own. So all that happens because you have access to the satellite constellation, without which nothing would be possible. Yeah, right. So in India, we have had a very rich cultural heritage of time measurement. So these are different kinds of time measurement systems that have been there. This is the famous Sun Temple in Konark, right? This, in fact, is a picture taken from Ayuka, Pune, right? And then we have the various Jantar Mantars in Jaipur and Delhi, and some of you probably have visited these places, right? So what is interesting is that a summary of these time measurement systems have been kind of very nicely put together in a nice article by Professor Shubhadeep Dey. He is also an expert in atomic clocks. He is in Ayuka, Pune. So the question then is, who needs a better time? And the answer is obvious: everybody, right? Whether you talk about applications in any kind of thing, right? I want to book a railway ticket. There are 100 seats. There are 1,000,000 people. How do I know who gets the ticket, right? So I need extremely fine time stamping to decide who gets the ticket, right? Same with the Bombay Stock Exchange, right? There are thousands of trades being traded, and there are some trades which are more popular, and those trades are basically bid by a lot of people. And so how do you decide who gets to win that trade, who gets to win the bid? It's only possible if you have very precision timing, and then only you can say, okay, this person bid first and this person bid second, right? So obviously satellite navigation is the hallmark of time measurement applications, and this comes under the domain of PNT. PNT stands for position, navigation and timing, right? So for any country, PNT is a strategic asset, right? If you want to cripple any country, you simply disable their time measurement system and everything will collapse, because without timing you cannot fly aeroplanes, without timing you cannot run your ships, without timing you cannot operate your banks, without timing you cannot operate your postal services. Everything crashes, right? So government realizes this. Actually, the government of India has actually put up a policy plan to secure PNT, because there's a lot of hostile neighbors around our country, and so it's very important to protect this as a strategic asset. We talk about deep space missions, right? So for example, ISRO, is sending spacecraft into Mars, Venus, and so on and so forth. And so beyond the Earth's circumference, okay, beyond a certain height, okay, you don't have access to GPS signals. So then how do you navigate in deep space? So what happens is there are these, very sophisticated looking radio antenna. So ISRO has something called the ISDN, which stands for the Indian Deep Space Network, IDSN actually, sorry. So IDSN is a small facility on the outskirts of Bengaluru, about 40 kilometers actually. And so if you go to that facility, it's a heavily guarded place, that's a different story. But if you go to that facility, you will see a whole bunch of radio antennas, and they're all pointed upwards. They're all tracking satellites 24/7, right? So all these PSLV, GSLV, whatever rockets we have, which are flying satellites, so these guys' job is to monitor the movement of those satellites 24/7, right? And so this facility also tracks, the rockets which fly into outer space. So ISRO has been doing this Chandrayaan mission, Mangalyaan mission, right? All of those actually are tracked by this deep space satellite network, right? And so what these do is basically they send radio waves, and these radio waves are precisely synced in time. And what is most interesting is that all of this, okay, whether you talk about a GPS satellite, whether you talk about how to maneuver a spacecraft, okay, apart from timing, okay, there is special relativity built in the motion and the trajectory of the satellite. There is general relativity corrections on the motion and trajectory of the satellite. So it's a very involved, very complicated system. Okay, it's not very trivial, right? We're talking about quantum mechanics. Forget quantum mechanics. Classical mechanics can be equally dominant. Okay, so okay, then we talk about transport. Yes, obviously, we talk about stock exchange, right? I highlighted that one as well. E-commerce, right? Everybody is buying something or the other on Amazon and Flipkart and so many other things. Once again, everything gets tracked in real time, right? You select something, you say, okay, I want to pay, and then 10,000 options will come before you: debit card, credit card, blah blah blah, and then you say, okay, I want to pay by phone pay, right? The moment you register your payment, what happens is there is a timestamp associated. You can check your phone pay accounts, okay, you can see, or even your Google Pay accounts. If you look at the invoice, there's a timestamp, there's a date, everything is very accurately mentioned. And what is most fascinating is that these atomic clocks could also be used for fundamental research. So what do I mean by fundamental research? So in modern physics, there are a lot of unanswered questions in physics, right? So what answer questions? One of them connects to dark matter and dark energy. So if you look at the universe around us, and if you look at the total matter content, what you find very surprising is that the total energy content, okay, the known matter is less than 5%, right? There's about 24% dark matter and the rest is dark energy, right? And so all the periodic table, all the standard model, everything is less than 5%, which is very funny because it's all complicated. Every now and then somebody says, oh, we have found a new element, right? Okay, very good. But then that is still within this 5% bracket. There's so much things which we don't know, right? And so the question is, is there a way to understand what kind of particle or what kind of field actually connects to dark matter or dark energy? This is a very open question in physics till date, and one of the most foremost problems in physics. The normal matter, okay, which is coming from heavy elements, neutrinos, stars, all that, right? All of that composed, okay, is around this area, and then the rest of the circle along with this part is about dark matter and dark energy, right? And so there's a big question in physics, okay, what are the particles or what are the fields which are unknown to the standard model, which will give us some idea on the nature of dark matter or on the nature of dark energy. And the question comes from a very interesting observation. So what happened is around, I think, 1930s, somebody was actually looking at the velocities of gases in the center of the galaxy, right? They were monitoring the speed of the gases. And what they observed is that as they moved out from the center of the galaxy towards the outer edges of the galaxy, the speed, as per Newtonian mechanics, should actually come down, but it did not come down. It maintained more or less the same value. And they said that this can only happen if there is some hidden force or hidden energy supporting this. And that is where they coined the term dark matter and dark energy. Right? And so there are various other instances: the cosmic microwave background radiation, large scale structures that form in the sky. All of them have signatures connected to dark matter and dark energy, right? And so the question is that, okay, there is a very strong, overwhelming astrophysical evidence that there's this dark matter, okay, because we are able to monitor the speeds of these gases, we are able to record the velocities, we can plot those curves, and it's a very unambiguous signature that something is going on, right? And so the question then is, what is dark matter and how does it interact with ordinary matter? Ordinary matter means the ones which we know from our periodic table or from the standard model, right? And whether there is some non-gravitational interaction between these two elements, right? So if you look at the Milky Way, we have a central bulge and there's a very big dark matter halo around the Milky Way, right? And so people have estimated the density of dark matter, the velocity of dark matter, right? There's a very nice review article, okay? And then what is interesting is that this question, okay, I have the dark matter or dark energy sector and I have the standard model sector. And remember, the standard model is a model. It's not a complete picture. There are various gaps with the standard model which are still not explained properly, right? So the question is, okay, is there possibility that we can have some kind of new interaction or new particle or new field that will tell us that how dark matter or dark energy can couple to the known standard model and give us some insight on the background and origin of these new hidden particles. So this is called beyond standard model physics, okay? And this is a very open question in physics, right? So now the interesting part is that, okay, how does atomic clocks come in this picture, okay? So if you think about it, let's consider this two-level atom, right? And now if I am able to measure this energy gap between these two levels with extremely high precision, then what happens if I am able to measure this energy gap with extremely high precision? If there is a small change, okay, because of some external perturbation, I would be in a position to be sensitive to that change, right? And so this is what the power of atomic physics builds, okay? So you have this extremely precise spectroscopy that you can perform with a laser, and if this is performed at a very high resolution, then I would be sensitive to the perturbations on the upper energy level. And so the idea is that the dark matter particle, which we are still not sure of, or the dark matter field, that is probably already coupling to this excited state, but that coupling is extremely weak. And so right now we are not able to understand that interaction. But if we develop enough resolution, if we develop enough accuracy in our measurement, then we start being sensitive to these changes and these couplings, and that is where the power of the atomic clocks lie. Because atomic clocks lie on precision spectroscopy, so precision spectroscopy can be a very effective tool in probing these hidden fields or hidden particles beyond the standard model that connect to dark matter and dark energy, right? So if you think about it, you have this quarks, okay, leptons and other things. These are all known things from the standard model. And so the question is, okay, if I am able to figure out how an unknown particle or field will couple to the standard model, if I am able to measure this change or the shift of this energy level, then I can figure out what is the strength of that interaction, and then I can do some math to figure out what is the nature of that particle and field. So this is the basic premise on which a lot of modern day research in atomic clocks is happening, right? So the other is to actually, completely revamp the standard system of measurement. So we are aware of the SI system. We talk about the kilogram, we talk about the meter, we talk about the ampere, and so all of these are based on different physical quantities, right? For example, the length measurement is tied to some bar kept at somewhere. The mass measurement is again tied to some mass kept somewhere. And so there was this international initiative which said, okay, can we actually revamp how we measure these fundamental units, the fundamental length measurement, which is 1 meter, time measurement, which is second, everything we connect to the second, right? And so what is the motivation for this? So Professor Arthur Shallow, who was a Nobel laureate, okay, I think some of you may have heard his name. So Arthur Shallow had once remarked, never measure anything in your life except frequency. Why did he say this? There's a very big reason why he said this. If you think about length measurement, let's say I want to measure the length of a bar. So if the environment in which you are measuring the length of the bar, if it's hot or warm, there is a chance that the bar expands. And so what you measure in summer will differ from what you measure in winter, right? And this can happen for other things also. Let's say if you want to measure the mass of an object very precisely, then depending on the local environment, the mass can change at a few microgram level, right? Now, what if I come up with a strategy such that all these other units, okay, are measured in terms of some frequency parameter? The advantage is that the frequency parameter is dependent on atoms, right? And atoms, okay, are universal entities. So whether I measure an atomic transition in Chennai and if I measure the same atomic transition in Tokyo, it's going to yield the same value provided the environment is controlled. And so there is this huge emphasis to revamp the entire SI system, the basic units, and connect them to the second, because this connects to a frequency measurement. So if you know, the current definition of second is connected to the measurement of the hyperfine separation in 133 cesium atom, right? And we'll come to that, okay? So what is a clock now? Okay, so what's a clock? So clock has three elements, right? So first thing is that we need something which exhibits periodic motion, right? This periodic motion can be to and fro motion. It can be a circular motion as well, right? For example, in earlier days, people used to say, okay, I take the rotation of the earth around the sun as some reference, and it's periodically. Every day the earth is orbiting around the sun, and so I can create a clock with that. Of course, that's a very poor kind of clock, because depending on the nature of orientation of earth with respect to the sun, the length of the day will change, right? And that's not a good thing. So we need something with a periodic behavior, which means that we need a system which cycles at a constant frequency. What are the other things? We need to count the cycles to produce a time interval. And the third thing is we need to agree on some reference. So if some system satisfies these three basic tenets, okay, of time measurement, then we can create a clock out of that system. That is the basic thing, okay? So now, if you look at this picture, this is the picture of the first atomic clock, right, which was created by Louis Essen in the National Physical Lab in UK in around 1955. So Louis Essen and Jack Perry, they were the creators of the modern atomic clock, and so this was accurate to about 1 part in 10 to the power 10. So in today's age, we have clocks which are accurate to about 1 part in 10 to the power 16, 10 to the power 17, 10 to the power 18, which means over the age of the universe, they will lose less than 1 microsecond. That is the precision that the current clocks have. This is amazing, right? You know, if you think about it. So, if you look at the evolution of clocks, starting from the modern atomic clock by Essen and Perry around 1955, this was accurate to about 1 part in 10 minus 10, and then you see there is a series of evolution of such clocks, and coming to 2020, we are hitting almost 1 part in 10 minus 16. So this is the current limit of cesium-based atomic clocks. In India, the National Physical Lab in New Delhi, they also have a cesium-based clock. And so what they do is they make measurements over a period of time, and then they send these measurements to an agency called the Bureau of International Measurements, which is located in Paris. And so this agency collects this time measurement from different other atomic clocks across the US, across Germany, across Japan, okay? And there's a complex algorithm, and then they say, okay, this is the universal time UTC, and with respect to UTC, this is what the Indian standard time should be, right? And that is how we get our IST, right? Of course, as Indians, we are very notorious of sticking to time, right? We never come to meetings on time, we're always delayed, and so IST has turned out to be some kind of a notorious acronym for us, right? That when you say IST, that means that fellow is going to be late, okay? You can be safely assured. Now, with hopefully with trains like Vande Bharat, whose doors close on time, you have seen probably YouTube videos where passengers get left on the platform, right? And hopefully this will help us improve in our time measurement and time management as well. Okay, so this is the current state of the art with respect to cesium atomic clocks. So the modern day timing systems are based on cesium atomic clocks. We have a cesium atomic clock in our country also, right? And so the Indian standard time is actually coming from such a clock. Right, and so what happened in 1967, very interesting development happened across the world. So the cesium clock was adopted as the basis of international definition of time, right? So what is this definition? Please note this definition here, okay? It says that the second so the second is the duration of 9192631770. It's a very specific number. You can see that it's a very specific number, and if you count the digits, okay, so how many digits are there? We have 3, 6, 9, 10, and that's what is 1 part in 10 to the power 10, right? So we are talking about this. We're talking about this 1 part in 10 to the power 10, and so this is coming from that number. So we are able to precisely measure this number to the first decimal point, right? And so this number is actually what? So if you look at cesium atom, it has got the ground state. Look at this frequency, okay? This frequency is in gigahertz, okay? It's in gigahertz. It's not an optical transition. It's a gigahertz transition, right? So what does it mean? It means that it's a microwave clock, right? Everybody has heard about the FM radio, right? FM radio operates from what? 88 megahertz to 108 megahertz. That's the range, right? So that's the range in this clock operates. So this is at 9 gigahertz, okay? 9.192 gigahertz to be precise. So this is a microwave clock. And so what happened was, people started thinking, is this the best clock that we can get? No, of course not. There are better clocks which have come into existence, and these are called the optical clocks, right? And so if you think about it, okay, the reason why we want to create the clocks out of atoms is because they are the same for all atoms of a particular species. The active clock is something where the signal comes directly from the radiation emitted by some atom or some ion. So what is an example of this type of an active clock? A hydrogen maser, an active hydrogen. So if you go to the National Physical Lab in Delhi, you have the cesium atomic clock, and along with the cesium atomic clock, you will see a whole bunch of other clocks, and these other clocks are all active hydrogen masers, right? So ISRO has a whole bunch of active hydrogen masers in their facility. There's a facility called ISTRAC, okay? ISTRAC is standing for Satellite Tracking and Telemetry, right? So what they do, they track the position of the satellite once it's kind of launched from the rocket, put into orbit. From that point, ISTRAC takes over, right? So ISTRAC is monitoring all the position of different satellites that India has launched, okay, and they are trying to measure different applications through those satellites, right? So when ISTRAC wants to send a command to a particular satellite that okay, the orbit needs to be corrected or changed, that is based on the hydrogen masers that are kept in this facility. So you have to be very precise on when you send the signal, because this is a radio signal that you send from your control facility to the satellite that is orbiting the Earth. So the action happens after a certain time. You need to take into account the relativistic effects that the Earth has, that the space around the Earth has on the satellite, in order to understand when the signal will reach the satellites, when it will be executed, or how long it will be executed, so on and so forth. And this is under the direction of these active clocks. There are also passive clocks, right? And so if you look at passive clocks, this is something that the optical clocks come under. So the optical clocks that people are working on, what they do, they take an atom or they will take an ion and they will try to probe a particular frequency gap between two specific levels using this laser. So that will be a passive clock, right? Now, this is how this of a modern day optical clock looks like. So what is happening? There is some reference which is a particular atom, right? There is a detector and there's an oscillator. So the oscillator probes this reference. You get some signal on the detector. there is some feedback to tell you whether you are on the right side of the transition or you're on the wrong side of the transition. And so you do this corrective mechanism, and then you take a part of that signal, you feed to a counter, and then you have a display attached to the counter which tells you the time. This is exactly how time is displayed. So if you look at an active hydrogen maser, it will have a 10 megahertz reference output, right? If you post a GPS antenna on your roof and you tap that signal, you will get a timing stamp at either 1 megahertz or 10 megahertz depending on the instrument that you're using, and you're actually measuring the time directly from the satellite. It's actually amazing how this thing works, okay? So if you think about it, all of this technology is already incorporated, okay, in the form of an experiment, and then the measurement is done. It's sent to this institute in Paris. They take data from several other such experiments around the globe, and they have this complex algorithm which then tell you what is the universal time standard. With respect to that, what is your specific country's local time? So they give a time to India, they will give a time to Japan, they will give a time to France, like that, right? So when you look at this atomic clock diagram, there are two parameters which tells us how good or bad this clock is. And what are these two parameters? One is called accuracy and the other is called stability. And while they may seem to be very closely worded English terms, but the implications are very different. So when you talk about accuracy, imagine there is this bullseye target, right? You have these rings, right? There's a red dot at the center and there are rings around that, and you start throwing darts. So if you miss all of the darts, if the darts are not hitting the center, then what it tells us that you are not accurate enough, correct? But imagine a situation where all the darts are consistently hitting a same point over and over again. That means you are consistent, you are stable, right? And this is exactly the two terms that affect the measurement. So you can see that you have this target frequency which you want to measure, and you are somewhat shifted with respect to the target frequency. So you are not very precise, but if you look at this signal, it's a very flat line, which means it's a very stable source. But in order to get a good clock, I need to be accurate as well as stable, right? And so here's this nice picture which shows us, right? You can see this picture here. You look at these four plots here, right? So this dashed line that you see, that's the reference frequency I want to measure. That's the measurement, let's say, coming from a particular atom or ion. Now if you look at the first plot, what is there? Some signal I have measured, but it's completely out of the reference point. So I have done a measurement, but it's not accurate enough. Yeah, I have a stable measurement, but it's not accurate. Second plot, everything is crazy. I am neither accurate nor stable. There's a lot of fluctuation in my measurement. Third one, I am accurate but not very stable. Why? Because you can see a lot of fluctuation on my measurement. The ideal condition is this one, the last plot, where I am not only accurate but also stable. And for all kinds of clocks, this is what is important. What is interesting here, and this is something that I'm not sure if you are aware of this. So all of you probably would have studied the simple pendulum in some form, either under waves and oscillations or under classical mechanics, right? You will have also studied about the LCR circuit, right? LCR circuit, AC current analysis. How many of you, right? I think most of you will have studied in high school, right? And then if you think about an atom, I have given you three examples. One is a classical pendulum, the other is this electromechanical resonator, right, the LCR circuit, and then I'm talking about an atom and ion. So what is the common thing that binds all the different oscillators? I talked about a classical oscillator, I talked about an electromechanical oscillator, I talked about an atomic oscillator. So what is the common thing that binds all the three? Absolutely, frequency. And so when you talk about frequency, what is very interesting, and this is something that I don't know how many of you have noticed, the way we approach the problem in the three cases is different, right? So if you look at the classical harmonic oscillator problem, the simple oscillator, the damped harmonic oscillator, all these problems are solved in the time domain. X double dot equals to something something something, right? So that X double dot is what? It's a time derivative. If you now go to the LCR circuit, so you will see that problem is not solved in the time domain, that's solved in the frequency domain, right? It's very interesting. And so when we read about this, we don't pay attention, right? Oh, this is just part of the syllabus, somehow mug it, okay? This is important, read that part. They gave the derivation last time, this will come again probably, okay? So all these questions come to our mind, and unfortunately what we miss is the connection. So what is the connection? Connection is Fourier transforms, right? So all of these solutions are basically two sides of the same coin. In one case, I'm solving the solution, I'm solving the equation in a time domain approach, right? I solve this X double dot equal to something. In the case of the LCR circuit, if you go back to your NCERT textbook, you will see everything is in terms of omega. There's no time component there, right? You talk about reactance, you talk about all other quantities, everything is in terms of omega. And then basically what happens is we don't realize that these two are essentially oscillators, okay? And what is most interesting is that there is this function called Lorentzian. How many of you have heard of the Lorentzian function? If you read about the Lorentzian function, what you will see is that this is the unique function which describes not only your simple pendulum, but it also describes your LCR circuit, and interestingly the same function also describes your atomic oscillator. That's the beauty. That's what physics is so, why is so interesting. So the same expression connects not only the classical oscillator, it also connects the quantum oscillator, right? So when I look at an atom and I measure the energy, okay, the separation between two levels, the line shape that I get is a Lorentzian, right? If I take this damped harmonic oscillator, which I solve in the time domain, right? Everybody remembers that formula, A e power minus bt, then sine cos something is there. If you take a Fourier of that, you take the real part, you will get a Lorentzian, right? So if you go back to your NCERT textbook and you open your LCR circuit discussion, you will see plots which are function of omega. They are not function of time. And you will see resonance curves. And if you look at the shape of that resonance curve, that's the Lorentzian function, right? It took me 30 years to understand what is going on, but now I'm happy that I figured out, okay, that what you study is presented in very different context, okay? And so you think that the LCR circuit is different from your simple pendulum. You think, oh my god, this is so many equations here, I already read so many equations there, again now this is in omega, that is in time. But what is most important is that there is something called Fourier transforms, and if you apply that, you can actually solve anything in complementary terms, right? So the time domain and the frequency domain are complementary terms, right? And so one can do this analysis and you can actually verify that this is true, right? Okay, so now coming back to the discussion, okay, let's go a little bit forward. Right, so how do you constitute an atomic clock? Well, you trap some atom or ion in some way. So if you want neutral atoms, one can use something called a magneto-optical trap, where you use magnetic fields and light forces to cool and trap neutral atoms. For us in Tirupati, we are working with calcium ions, so what we use is an ion trap, and so we use radio frequency fields to trap an ion. And so once the ion, and I'm talking about one single ion, right? So what is the size of a single ion? Human hair, if you look at the cross section of human hair, it's between 70 and 100 micron, right? And so if I want to image one single ion, that is less than 1 micron. So if I take a single strand of hair from my body, and if I try to look at the cross section, that itself is not visible, right? So forget about imaging an ion with a human eye, that's not possible. So you will need some specialized microscope imaging technology to visualize you have trapped something, right? And so there's a lot of involved experimentation involved, okay? So you take some atoms, you trap them, right, or ionize them, and trap it in a radio frequency trap, and then you want to measure the frequency difference between particular energy level, and for that you use a laser. And then what you do, once again, you remember there are three things that we need to do to make a clock. One is to figure out a reference, second is to interrogate that reference at a particular energy level, and then measure that and give the time. And so this is exactly what we do for an atomic clock. So this is the only equation I'm going to highlight in today's talk. So here, this expression tells us the sensitivity of the atomic clock, right? We talked about accuracy and stability. This is the accuracy or the uncertainty that is there involved in the measurement. So what are the quantities here? This is this quality factor. This is the number of atoms or ions involved in the measurement. This is the measurement time. This is the averaging time, right? And so this is the only thing I'm going to show today as mathematical expression, nothing else. So you see this quantity delta nu by nu naught. This is 1 by quality factor. Why is this important? Because if you think about it, if I have the same delta nu, but if I change this value nu naught, if I go from microwave to optical, so microwave frequency 10 to the power 9 hertz, optical 10 to the power 14 hertz, 5 orders of magnitude difference, and immediately for the same delta nu, the quality factor improves drastically, right? And so what is the physical significance of the quality factor? Remember, the quality factor tells us how good or bad the oscillator is, right? So what is the significance? It means that if I put a certain energy on the oscillator, how rapidly is the energy decaying? If I have a very good oscillator, if I put certain energy, that oscillation is going to sustain for a longer time. If it's a poor oscillator, it's going to sustain for a shorter time. And you can understand this through this example. We had these pendulum clocks, right? And every 4 hours you have to crank up the spring, right? So the spring, the winding on the spring, the tension on the spring would loosen up and the clock would start to lose time. Then we went to the quartz crystal watches, right? So what was the advantage? The quartz crystal was a much better oscillator. So when you pump energy in the quartz crystal, things would be stable for almost a month or so till the battery starts decaying. And now we are talking about atomic clocks where virtually there is very, very little shift, extremely small shift, right? And so if you think about it, the idea is to go to smaller values of delta nu. The idea is to increase this nu naught. And so what is the solution? I want to move from a microwave time measurement domain to an optical time measurement domain, right? And so you can see very clearly the microwave is about 10 to the power 10 hertz, is about 10 to the power 15, and for the same delta f, the quality factor changes very dramatically, right? And so the Q factor is about 10 to the power 15 or even higher depending on what type of transition it is, right? So this is a small schematic, simple schematic of how an atomic clock works. You have the reference, you are measuring some energy level gap using a laser. A part of that laser goes to something called a frequency comb. Okay, this technology was awarded Nobel Prize in 2005 to John Hall, okay, and Theodore Hensch in Max Planck Institute of Quantum Optics. So a part of that laser, okay, is going for feedback. You put it to the comb. The comb is like an optical ruler, right? It's like an optical ruler. Just like I have a physical ruler with markings and I can measure the length of something, I can use the comb and you can see here different lines of different colors. And these lines are extremely narrow and very precisely positioned. And so I have this comb, and with that comb, I can actually measure any frequency very, very accurately. And so what it does, it actually measures its optical frequency and converts that to a usable radio frequency. Remember, all timekeeping devices in today's world, they are all either 1 megahertz reference or a 10 megahertz reference. Okay, and so these guys, okay, Theodore Hensch and I think John Hall, okay, they were the pioneers of creating this optical frequency comb and enabling the optical measurement to be transferred to the radio frequency domain. And that is why, okay, this experiment or this technology is so vital. If you look at pictures of how this time measurement was done, okay, in the late 1960s or 1970s, there was a room completely filled with electronics just to measure something from the optical to the radio frequency domain. Now you can get a frequency comb which is basically the size of your computer cabinet, and you don't need such kind of heavy electronics anymore. It's all compact and form factor. So what has happened, you have some optical frequency and there's some gear system which translates this frequency to the microwave output which you need. Okay, and so here you can see, okay, this nice plot where you started with Essen's clock in 1955. This was the microwave clock, the first clock, 1 part in 10 power minus 10, and then around 2010, okay, the optical clock started making a difference. And so what we see is that right now the precision is about a few parts in 10 power minus 18, right? And so the JILA group, okay, this is Joint Institute for Laboratory Astrophysics, okay, this is Professor Jun Ye is there, and in PTB there are multiple PIs. Professor Pete Schmidt is there, okay. Their groups are focused on improving the time resolution measurement using optical clocks. So in our case, as I said, in Tirupati, we are using a single ion. What is the ion that we are using? We are using calcium ion, right? And so what we do, we use this ions for measurement of the frequency gap. And so what is the advantage? So in ions, okay, especially in 40 calcium, there is this clock transition which connects to a metastable state. We all know what a metastable state is. A metastable state is something which has a long life. Why is it advantageous? Because if you remember, there is this energy time uncertainty, delta E, delta T, right? So if time, the lifetime is more, if delta T is more, then delta E is small. If delta E is small, that means I have a very narrow transition. And if I have a very narrow transition, I can use that as a reference, right? That is the whole point. And so if you think about it, I can create this ion trap, basically 2 electrodes which have some radio frequency. I trap this ion, this green dot, and I can use a bunch of laser beams to cool the ion. And so once the ion is cooled enough, I can do spectroscopy on this cold ion and attain this precision that I was showing on these different plots. So what is the advantage here? If you do this measurement in an ion trap, there are multiple advantages. First of all, you don't have the first order Doppler shift. Secondly, there is a minimum second order Doppler shift. Third, these field perturbations are minimized at the trap center. And fourth important point, the background collision rate is very low because you have only one guy sitting at the trap. And so if you think about it, okay, here's this ion trap potential. All of you have heard about the Earnshaw theorem, right? So what's the Earnshaw theorem? It says that you cannot trap a charged particle by static fields alone. So then people did something clever. Okay, then I can rotate the field, and so I create a dynamical equilibrium. If I ask you to sit on a cycle, very difficult to sit straight. But if I ask you to pedal the cycle, you immediately maintain balance, you don't fall. Exactly the same thing here. If I have a static field, the charged particle will slip this side or that side. But what if this field moves at a very rapid rate such that the moment the particle tries to flip on the other side, it encounters a rising potential. So then what happens? It's always in this dynamical confinement, right? So I can create something like a saddle potential, right? You have seen the horse, right? And you've seen the saddle on the horse. So imagine the saddle which is rotating rapidly. That is the saddle potential that gets created by putting fields on this ion trap electrode, right? And so you can trap something there, right? And so now coming to the question, why do we use calcium ion? Remember, calcium ion has multiple isotopes, right? And so one of the major advantages is that one can use this multiple isotopes for something called the new physics measurement. right? Apart from the new physics measurement, there are other advantages. One of them, and the most important one, is that if you look at the energy level structure of this calcium ion, it's a very simplified structure. It's not complicated. So if I want to create a portable clock, I need something which is compact. I need something which is simple, right? And so if I choose an ion which has a simple energy level structure, it simplifies the technology challenges. And that is why we have chosen calcium. The other advantage is that you have lasers which are commercially available at low cost to cool the ion. Third most important, you have multiple isotopes to probe isotope shifts. And from these isotope shift measurements, one can try to understand if the new physics is there connecting to dark matter and dark energy. Okay. Finally, okay, the ion trap that we are using, okay, we operate the ion trap in something called the magic RF frequency. What is the importance of this magic RF frequency? The important thing is that at that frequency, we will be able to cancel the micromotion induced shift with the second order Doppler shift. That is the advantage. There is a magic frequency that happens even for neutral atoms. As I said, there are two kinds of optical clocks. Some of them use neutral atoms, some of them use ions. We are using ions in Tirupati, but there are groups in the world which also use neutral atoms. So what they do, they cool and trap these ions and put them in an optical lattice. What is a lattice? You can imagine an egg crate structure which is created because of the interference of laser beams. You have pockets of local minima, and these pockets of local minima, you can trap these atoms like billiard balls. That's a lattice. Now, problem is that this lattice itself is adding some shift. And so, Professor Katori from the University of Tokyo in Riken, he came up with this very, very interesting idea that what if we use a laser beam, okay, of a particular frequency that is able to eliminate the AC start shift, and that is where the concept of magic frequency was born. Okay, so in ion traps also, we can use this RF frequency at a precise value, which is called the magic frequency, and that will cancel the micromotion shift with the second order Doppler shift. So this is the actual picture of the ion trap that we are using. You can see it's a very polished electrode. There's the ion. There's some of the electronics that we have developed, right? I'm not going into details of the ion trap parameters, but what is important to note here is that this ion trap technology was awarded in Nobel Prize in 1989. Okay, so Hans Diemelt and Wolfgang Paul was awarded the prize, and our objective is to create a system like this. It's a very compact system. Everything is transportable. And why are we trying to do this? Okay, there are a lot of applications which require precision time measurement in a real world environment out of the lab. For example, there is a series of radars that are connected or that need to be connected across the border, right, for surveillance application. So those radars will be synced with such a clock. Let's say we send a spacecraft to some object in space, okay, and it's a very far away space exploration that we have taken. So the deeper you go into space, the finer you have to measure time. And so once again, this kind of a atomic clock package, a portable clock package, will be very useful, right? And so you can see once again, this output is in terms of 1 or 10 megahertz, right? So here I come to the end of the lecture, and I would like to acknowledge my collaborators across various institutes in India and abroad, and my students Rishabh, Vikrant, Himanshu, Purvisha, and postdocs Nadeem and Ashok. And so this is the picture of our group taken in our lab. So you are welcome to visit our lab. If you are coming to Tirupati, please visit our lab at IIT Tirupati. We'll be happy to show you around and explain some of this technology. Okay, it's a very interesting field, atomic physics. Okay, and with all the noise that you hear about quantum computing, it's something that is lost is the technology on quantum sensing. So time measurement comes under the picture of quantum sensing, and realistically speaking, efficient quantum computers, probably 10 or 20 years down the line, what we have is right now dirty quantum computers, but you are already living in the era of quantum sensing, because all of you are accessing GPS, and GPS relies on atomic clocks, right? Atomic clocks fall under the domain of quantum sensing. So while we are celebrating the year of quantum, and I think the year of quantum is going to end tomorrow or day after, I'm not sure exactly, but I think tomorrow or day after it's ending. It's important to note that we have been living in the quantum age for the last 50 years. It's just that we have not been aware of this thing. All of us have been benefiting from the advantages of quantum sensors, especially in precision time sensing. We take a lot of things for granted, but then it's important to highlight and make us aware that this is something that is very much part of our daily lives, without which modern civilization will cease to exist, right? So with that, I would like to end the discussion here. If there are any questions that you would like to discuss, I would be very happy to try and answer them.
Fantastic talk.
Thank you.
I have a question regarding this. You spoke about the 10 power 16 parts per second. So that actually we are doing with optical clock.
So one part in 10 power 16 is with the current microwave clocks. With optical clocks, we have exceeded that precision. We are about 1 part in 10 power 18 or 1 part in 10 power
18, 19. Yes. I'm just curious, if we need to go, I think with GPS and all this, we are able to do it very comfortably.
Correct.
If there is a need to go for a little longer, even more finer resolution.
Yeah. So
That is so, then is it in the outlook to go for UV, X-ray and gamma ray?
correct. No, so that's a very relevant question. We always ask that, okay, do we really need this amount of precision, right? That's a very pertinent question. So right now there are very few niche applications which will benefit from this precision. One is this domain of space exploration, right? So you may have heard about this technology called VLBI. VLBI is very long baseline interferometry, right? So very long baseline interferometry. With that technology, people were able to take the first image of a black hole. So you cannot take an image of a black hole because black hole doesn't reflect light. But what they did was they actually imaged the gases that were actually entering the black hole, and the radiation emitted by the gases, because they're going inside, they're charged, right, they're radiating, so they imaged that, right? So this was done with the Event Horizon Telescope, right? And so the idea of VLBI and using VLBI to probe primordial light. So what is primordial light? Primordial light is something that is just few let's say seconds after the Big Bang, right? So the whole concept is that there was this Big Bang and the universe started with the Big Bang, right? And so why is people interested in LIGO? The reason people are interested in LIGO is because LIGO enables us to look, back in the past, okay, and remnants of that history. How did the universe evolve? So a lot of this technology actually relies on atomic clocks, right? And so this VLBI is one technology. Space exploration, sending spacecraft, sending space vessels to different other planets, that will require communication, that will require guidance, that again benefits from such precision. And of course there is a very big fundamental physics angle to all of this, right? So I think probably last year sometime around May or June, I don't remember the exact month, there was a result from the Jilla group where they were able to measure the gravitational redshift. Okay, when they lifted the experiment by 1 centimeter, they could measure the gravitational redshift on the atoms that were trapped. So that is remarkable. That means that your measurements are so sensitive that even if you lift the experiment by 1 centimeter, the local gravitational potential is showing some difference on the energy level, right? And if you keep pushing the limits, if you keep pushing the boundary of precision, there is a high chance that we will reach this sensitivity level, which leads us to this insight into dark matter, right?
So that is in the pipeline.
That is in the pipeline. Yes.
Trying to go into the final resolution.
Right.
Now I invite Mr. V. Suresh Kumar of 3rd BSc Physics to deliver the vote of thanks for the session.
respected dignitaries, faculty members, and friends, on behalf of Department of Physics, Dwarakadas Govindas Vaishnav College, I honored to propose the word of thanks. We extend our deepest gratitude to our speaker, Dr. Ajit Sharma sir, Associate Professor from IIT Tirupati, for his fascinating session on Sundials to modern atomic clocks. Sir, we thank you for your taking us through the incredible evolution timekeeping from ancient sundials to high precision atomic clocks and sharing your valuable time and expertise as part of this national colloquium on quantum science education. Once again, thank you, sir.